right, honors physics, back into action here. So we finished up on this slide before. So just noticing this idea, like the fact that the planet, or in this case, the satellite, is going around the Earth, is because it's being redirected in by this constant force of gravity. Okay. So let's jump into our next slide. So Isaac Newton came up with this hypothesis about universal gravitation. And one of the ways to explain this is imagine if you had like a cannonball and you were to shoot a cannonball off a mountain. Well, it would just naturally go outwards and then fall. Okay. And then he thought, well, what if you shot it so fast that it actually shot off and went off into space and never came back to the Earth? Okay. But what if there was a spot in between those two things where you shoot it off with just the right speed, that it's going fast enough sideways that it doesn't fall back to the Earth, but then it's also being redirected towards the center in a ratio that allows it to effectively fall around the edge of the Earth, but never actually get closer to the Earth, it just maintains a constant height. That idea is basically what we call orbit. And when you notice the idea of orbit, it's because you have this gravitational force pulling the object back to the center of the Earth. It's accelerating it with g, acceleration of gravity, towards the Earth. But because of its sideways tangent velocity right there, it always manages to stay away. So it's kind of like flying away from the Earth, being pulled in the same ratio, and that balances out to create what we call orbit. So we're going to be looking at orbits a lot with this gravitational idea. Now, the big formula that we're going to be focusing on is this force formula right here. So force equals gmm over r squared. Now that formula there is a formula that solves for force. We've also seen centripetal force. We've also seen the weight force. We've also seen the friction force. We've also seen the normal force. There's lots of forces. This is just another force. And a lot of what we're going to do with this force is we're going to be replacing gravitational force for another force. And you're going to see that down in these speaker notes over and over again. That's how we practice these problems and we figure things out. Now, in the formula itself, there's this thing called G. It's called the big G as opposed to little g. And it's the universal gravitational constant. It has this value in these units right here. And what it really means is just like every bit of matter, has a little bit of gravity. It's universal throughout space. Like one atom has gravity. And then when you add all the matter up, mass 1 times mass 2, the product of these masses, you get more and more gravity. And then as you get further away from an object, this radius increases, this distance between you and a different object, gravity drops off as the square of the distance. So you're going to want to be looking at this formula, going to it a lot. Okay, I've worked out some problems now. What is the gravitational field strength? And I've shown you the work here. Okay, these are all going to be practicing for our practice problem set. We're looking at this idea of gravitational field intensity. Okay, this is basically what we've called up to this point, just G, like little g. What is the gravitational acceleration? At the surface of the Earth, that's 9.8 meters per second squared. But that changes depending on elevation, going far above the Earth. It also changes on other planets. And so all of a sudden, this g becomes this variable thing. We call it gravitational field intensity. And you can derive it from the formula force of gravity equals gmm over r squared. And when I define force of gravity as mg, force equals mg, I can see I can do some cancellation by little m's. I got g equals. So you're going to mess with these formulas. Looking at the inverse square law, I can do some proportional math to mess with those formulas. Gravity at work right here, we're going to look at how work is actually not done. So you're going to see that no work is done when you're going through an orbit because of conservation of energy ideas. So you're going to explore that. Okay. Kepler's third law is when we use the gravitational formula and we set it equal to the centripetal force formula, and we realize that velocity is in there. And velocity, because it's made out of circumference distance divided by time, all of a sudden we introduce the time variable into it. And Kepler's law is just manipulating these formulas right here to look at the relationship between the orbital time period, like for the Earth going around the sun, it's a year, compared to the average distance. And we notice this formula that we call Kepler's third law. So anyway, my video is about to end again, so I'm going to go ahead and go to the third video here. So.